So kind of the idea for today, this first part of the lesson, I'm going to do some more examples about kind of going from a value to proportion under the curve, and also going from a proportion under the curve back to a value. It's very similar to the things that I introduced last week, as far as using like your z-score, finding the proportion under the curve using the standard normal curve. And I'm going to show you how to do that using table A today with these examples. So if you're still kind of learning how to use table A, there'll be some more examples of that today. And also how to use your calculator to find these things, which can also be very useful. So we're going to get started. If you're taking notes, you may want to take notes about how I do this. My idea for today is that I'm going to do these problems and verbally kind of walk you through what I'm doing and why. And then when I get to the end of the problem, I'll ask you if you have any questions or if you need anything clarified, if you need me to review anything that I did that maybe didn't make sense. So it shouldn't take too long. But yeah, hopefully you'll find this helpful. And not just odd that I'm sitting here doing math. So, here we are. Our context here, we can answer questions about area in any normal distribution by standardizing and using technology. I'll show you how to use your TI-84 graphing calculator to do these things today. We have some examples. All right. So our first example here. Right. On the driving range, Tiger Woods practices his swing with a particular club by hitting many, many balls. Suppose that when Tiger hits his driver, the distance the ball travels follows a normal distribution with mean 304 yards and standard deviation of 8 yards. Okay, so mean of 304, the standard deviation of 8. I've got that over here in our notation, the n parentheses 304 comma 8. And I've drawn the curve. I didn't actually draw that curve. I found a picture on the internet and I pasted it into this and then wrote the numbers I needed underneath it because I can't draw a line that smooth. So we want to know what percent of Tiger's drives travel at least 290 yards, right? And that means 290 yards or more. All right, so that means that so 290 is probably somewhere around here on our curve. All right, this is probably 290, or at least an estimate of where 290. And if I want 290 or more, I'm looking to the right of this point, right? I'm looking over here. Not to the left, which means when I find this value on table A, I need to subtract that from 1. I don't need what's to the left, I need what's to the right, which would be 1 minus whatever proportion is to the left, which is what I find on table A. So it's important to kind of make that distinction before you start doing the work so that you understand what you're looking for. So now we're going to standardize this score or this value to a z-score so that then I can use table A. So to do that, we have z equals 290 minus 304, the mean, divided by the standard deviation of 8. That's going to be a negative 14 divided by 8, which then, since I did this in first period, I already know, is a negative 1.75. So this is the z-score that I will look up on table A. So we need table A. So where did I put my table A? It is over here. There we go. All right. So I'm looking for a negative z-score, so I'm in the right part of the table. It's a little bigger. That works. All right. Yeah. So I start by finding negative 1.7, kind of the root. And then 5, the other part of the decimal, negative 1.75. All right, and then I find where they intersect. Right, 0.0401. So that means that is the proportion out of 1, right? 0.0401 that is to the left of that z-score. So I get 0.0401. And as we said, this is proportion to the left of negative 1.75. So to find the proportion to the right, we subtract that from 1. And that's going to be what I have a trusty calculator for. We get a 0.9599. So my proportion that is greater than or equal to essentially 290 is 0.9599. And I need this as a percentage. So we have 95.99%, or we can say approximately 96%. All right. And this is the percentage of tigers drives that travel at least 290 yards. All right. Now, this answer seems to make sense, right? We should have a large portion of our area under the curve counted in this like blue area here, right? It's definitely more than half and most likely more than 75% just by looking at it. But let's be certain. Let's use our calculator to also verify this answer. Which I have something there. There we go. All right, so our calculator can tell us the area under a normal curve. With a few clicks here, we'll go make this bigger. So we'll hit second and var. This var is above it. You see in blue it says DISTR distribution. I want the second option on this screen here where it says normal CDF. Okay. And I need negative 1.75 as the lower bound because I'm looking from that point and greater. For the upper bound, I'm actually just going to use an unreasonably large number to make sure I don't leave anything out because I don't have essentially a cutoff on the upside. I just want everything greater. So an unreasonably large number for this data set. Since this is a standardized score, we use the mean of 0 and standard deviation of 1. And we will hit paste and hit enter. It puts it into my normal calculation area and hit enter again. And we get 0.95994, blah, 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 this whole big decimal. Your calculator has more, like essentially more of table A saved into its memory than we have access to on our table A. So we get more decimal places and such. So this is the same thing we got for doing it by hand, but our calculator did it for us, hooray! Now we need to be able to do this work that we've shown here because most likely on an AP exam, they will ask you to show your work on how you got that proportion. The calculator in this case can serve as a way for you to have confidence in your answer, right? So that you're like, oh yes, I did this properly. I have the same thing that my calculator have. I verified my response here. Also, there may be cases where you just straight out, it might be multiple choice and you need the area under the curve, right? The proportion under the curve. This is a way to do it. All right. Any questions so far? Anything I can clarify? Okay. Is it okay if I go to the next example? Doesn't even need time to write anything down. So our next one here, we want to know, again, the percent of tiger stripes travel between 305 and 325 yards. Again, if we look at our graph here of the distribution, again, we'll pretend that I can draw a straightish line. It's very hard to do on this. So we're at 305 to 325 is going to be like somewhere over here. All right. So we have this. We want the area between these 2 points. All right. So it's going to be a little bit less than 50% because we don't have the entire area to the right of the mean or to the left of the mean. We've got it slightly inside. So it's going to be less than 50%. So we can use this again, kind of looking at the graph and getting an idea of what our answer should be is helpful for us to identify if we've made mistakes. Like if I end up with 60%, that doesn't make sense for where we're finding, the area we're looking at. So it can help us decide if we have made an error. So let's have a look at this one. So the first step is to standardize our scores again, or our values. So the z-score for the 305 yards, say 305 minus 304 divided by 8. It's going to be 1/8, which is 0.0125. And then our z-score for the upper bound is going to be 325 minus 304 divided by 8, which will equal 21/8, which is 2.625. Right, so these are now the z-scores. For table A. Okay. Now, the issue with these scores, with these z-scores, is that, oops, that way, on table A, I only can go up to essentially 2 decimal places. I think I made a mistake here. Too many zeros in the decimal on the first one. Yep. Good. All right, back to our regularly scheduled programming. In this case, we only get 2 decimal places. So we're going to lose a little bit of accuracy because I can only use like 0.12 or 0.13 for the first one, or 2.62 or 2.63. Since the following decimal place is a 5, I technically should round up to use 0.13 and 2.63. Because on table A, that's as close as I can get. So we have 0.1 for our first one, and then 3, which gets me here, 0.5517, and then 2.63 again, we'll use the 0.03. So I find 2.6 as the root, and then the 3, and we get 0.9957 for the upper bound, right? So the 0.9957 is the proportion of the area under the curve to the left of that z-score, and the 0.5517 is the portion of the curve to the left of that smaller score. I need what's in between, so I'm going to subtract the smaller proportion from the larger proportion. All right? So that will be 0.9957 minus 0.5517, which gets me 0.444, or 44.4%. Right. Just again, it makes sense for my picture. Right. We knew it should have been less than 50%, so that works. That helps. All right. So we can say that approximately 44% of Tiger Woods drives are between 305 and 325 yards. Right. We can kind of round it to an approximate right there. Also, we can look at what happens when we do this in the calculator. In this case, we'll go back to this second option here. And now I have a lower and upper bound. So I'm going to put those both in. So I have 0.125 and 2.625. In this case, I don't have to round off any of that decimal. I can keep it all. This in. We get a slightly different answer. Right? We get 0.4459, right? And this is due to the rounding that we had to use to use table A. Right? There's a slight bit of rounding error that happens. It doesn't mean that what we did is incorrect. We used the table. Right? We got our values. We would have gotten a slightly different value if we used the 0.12 or the 2.62. But we had to make that choice of kind of like which way to round. So using the calculator, right, we got basically 44.6%. So we have table A here, and we got 44.6% using the calculator. All right. Now, again, it doesn't mean either one is wrong. It's just two different methods. They're incredibly close, which means we didn't really make an error, right? We're almost the same numbers. You would be concerned if you were like 5-6% off, right? We're less than a percentage off. Right? If it's a larger percent off, then there's probably some issues going on. All right. Any questions on this example? Again, I'm using the calculator to verify my work, to kind of build the confidence in the calculations that we're doing. Anyone need a moment to write anything down? Okay. All right, in our last example here, we're going to be going the other direction, so to say, and go from a proportion back to a value. Okay, so we're starting here with our context of high levels of cholesterol in the blood and increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal, with mean mu equal to 170 milligrams of cholesterol per deciliter of blood, milligrams per deciliter, and standard deviation sigma equals 30 milligrams per deciliter. What is the first quartile of the distribution of blood cholesterol? All right. The first quartile goes along with the 25th percentile, right? The first quarter, so to say. So this is 25th percentile. We can see that as 0.25 as a decimal. The proportion to the left of the desired value. So I'm looking for the value that shows me where the 25th percentile is, and to the left of that is 25% of my proportion. Right? On this distribution, it's kind of difficult to see where that is when we're just looking at the curve. I know that right in the middle here is the 50th percentile, right? And I could maybe fill in some of the other percentiles using the 68, 95, 99, 7 rule. That's more time than we want to put into this problem, right? And we don't want to do the extra work if it's not necessary. So what we do, we say, okay, well, I know that I'm looking for a 0.25 value within table A. Okay, this decimal here, I need to find this in table A. And when I say in table A, I'm meaning within the body of table A. This is not found in the Z part, it's found in the interior. The 25th percentile will be to the left of the mean, right? It's less than the 50th percentile. So I'm going to be looking at negative Z-scores, which means I'm going to go up to the negative ones here. Right. Green. All right, and I'm looking for something as close to 0.25 as I possibly can find. All right, you know, we're close to 0 here. This other corner gets close to 50%. I'm trying to find something in here. So if we look here, we're at 24, 23, 23, 22, 24, 24, 25. All right, so we go from 0.24 to 0.25 between these two numbers. So then again, I need to ask myself which one is closer to 0.25. All right. This one, right to the right here, is 0.0017 away from 0.25. The one over here is 0.0014 away. Right? That means this one wins. It's closer. So I now follow that one back. Negative 0.6 on the left-hand z-score, and that goes up to 0.07 on the top part for the second part of the decimal. So I have a z-score that goes along with the 25th percentile, or about 0.25 proportion of the area under the curve, at negative 0.67. All right, that's going to be the value of z. Now I can use this to work backwards in the z-score calculation to find the value that goes along with the 25th percentile, which means I start with negative 0.67, and I set that equal to x minus 170, right? The mean, divided by 30, and I solve for x, right? So I'm going to multiply by 30 on each side and then add 170, which leaves me with an equation that will look 30 like this. And we end up with we get 149.9. And that number gets the units from the original problem because that's what we just found. All right, so the 25th percentile of the first quartile, Q1, for the distribution of blood cholesterol is 149.9 milligrams per deciliter. Right, it's essentially what we found was the value of Q1. All right. What are your guys' questions? What can I help you understand better? What can I go over again? Was this helpful in being able to do these calculations? You just see how they're done. All right. So, last thing we're going to do is a quick presentation on assessing normality. Essentially, because normal distributions behave in such consistent ways, right? And there's ways that we can find more information out about normal distributions and normal curves. We have our table A and things like that. It's very useful to know if something is normal or if it's approximately normal, because then we can use all these tools. So that means we need to be able to assess normality, or if something is approximately normal. Okay. Why normal? Normal distributions provide good models of real data, such as SAT scores, IQ tests, and employment rates, etc. The distributions of some other variables are usually skewed and therefore distinctly non-normal. And yes, I think I misspelled, therefore I missed an E on there. Examples of these things are personal income, a lifetime of electronic devices, and other things. It is very risky to assume that a distribution is normal without actually inspecting the data first, which means we need a strategy for determining if a distribution is approximately normal. Right? Because if we can say that it is approximately normal, then we can use all these fancy tools that we've just been playing with. So that leads to, is this normal? First step will be to plot the data. Make a graph, put it in your graphing calculator, make a histogram, right? Dot plot, make a stem plot by hand. Then ask yourself, is the distribution symmetric and bell-shaped? Right? If it is not, then it's not a normal distribution. It fails the first part of the test. If it's skewed, it is definitely not normal. If it is bimodal, not normal. If it is symmetric and bell-shaped, it passes the first part, and then we need to check whether the data follows the 68, 95, and 99.7 rule, which means we take, proportions of data between the first, within one standard deviation, divide that by, the total number of data points we have, and make sure that that's somewhere close to 68%. All right, takes a number of data points between between two standard deviations, -2 and +2 standard deviations, divide that by the total number of things we have, should be close to 95%, and then again for 3 standard deviations. If it does not get close to the 68, 95, 99.7 rule, then it is probably not a normal distribution. If it's close, meaning it could be like 65%, 66%, and then 97 or 94%, and then 99, then 100%, 98%. If it's close, doesn't need to be perfect on these numbers, but it's close. Then we have good evidence that the distribution is close to normal or approximately normal, and we can more comfortably use some of these tools to evaluate our data or describe our data further. Right? So make a graph, right? Make a visual so you can see what the data looks like. Is it symmetric and bell-shaped? Does it follow the 68, 95, 99.7 rule? If it does, we can say that it's probably approximately normal. Okay. If you're still not sure, you've done these things, you're like, it's really close, but I'm not sure, we can also use what's called a probability plot. You do not need to be able to describe how one of these is made for the AP exam, but it is a tool you can use to help have confidence in saying something is approximately normal. And what this does is essentially plots points so that they are linear, make something that looks like a line if your distribution is approximately normal. And they will not really look linear if it's not approximately normal. And that's essentially what this little blurb here from the book says. If the points on a normal probability plot lie close to a straight line, the data are approximately normal, normally distributed. Systematic deviations from a straight line indicate a non-normal distribution. Outliers appears points that are far away. What this looks like, and there are directions in the textbook on how to do this, and a video that I have in the course resources. So what this looks like is if you have already put some data in, such as I have the unemployment rates for all 50 states that were provided previously in the textbook. I have those points put in here already. The same way I would put in the points if I was making a histogram, right? I can then go to my stat plot, and instead of telling it to make a histogram, right, I turn this one on, right? The histogram would be this one, right? And L1 and this and that. The one that's our last option to the right of our box plot here, this is the probability plot. So if I choose that one, I need to make sure that it's using the correct data list. These other two options you can leave. This is X and this is this point, this mark. That's fine. Next, you'll go to Zoom. So we're going to choose Zoom Stat. Right, it's the 9th option here. What that does is it makes it so that whatever we're graphing using our statistics will fit. We'll be able to see it in the window. I don't have to mess around with the window numbers myself. The calculator will figure it out. So if we hit enter there, it's going to think, and it's going to make this plot of points. This plot of points shows that it's about looks pretty much like a line. It's going in a very standard pattern of a line. And so that gives us more evidence that this is approximately normal. Okay. So if you've already gone through the trouble of putting the list in and making a histogram, you can also create this graph with like a couple extra steps. All right. And that's it.